So hello everyone, welcome to the July edition of the LINCC Talk. Today we will have a presentation from the Pitt-Google Broker, and it's such a great talk that 3 people will present it to us. And those 3 will be, so first Michael Wood-Vasey will give a short introduction. He is a professor of physics and astronomy at University of Pittsburgh. And then Raen will take over. He's an application developer at Caltech IPAC who finished his PhD recently at the University of Pittsburgh. And then Chris Hernández will talk about some of the most recent work and future plans. He's a 3rd-year graduate student at Pittsburgh, and he's also developer for the Pitt-Google Broker. Okay, so Michael, why don't you take it away?
Great, thank you. Thanks very much for the invitation. And it's a pleasure to be here. So go ahead, next slide. The Pitt-Google Alert Broker, the Vera C. Rubin Observatory will conduct the LSST survey. This is a LINCC Tech Talk, so I presume that is a common understood, but I just feel obligated to say that. Next slide. And so we're going to present the Pitt-Google Broker as a way to distribute alerts and help people get science out of the transient and variable universe here. I'm going to say just a few words here. And then Troy's going to talk about the design and, well, I suppose not the struggles. People never want to hear about the struggles, but implicit when someone presents a design, always remember that there were lots of designs that didn't work and they had to spend the effort to figure that out. And some details about how to connect to our pipeline. And then Chris will end up with discussion, an example of deploying a classifier module. And I actually like this talk and the structure because Troy, Chris, and I are in 3 different zip codes in 2 different states. And part of the design principle of our broker is that it is modular with well-defined and limited communication paths. So next slide. So the basic goals, objectives back in 2019 were basically when the design specs for Rubin LSST said, we have a limited bandwidth to send out events. And I thought, well, wait, sure, the design documents are from like 2010, but it's 2019 and distributing information to the world has actually been kind of a solved problem and rapid high performance things, but it's easy to say that and harder to do the work. But our goal was the public alert data, which are public for LSST, should be public to everyone. And how do we make that work? That is certainly a guiding principle. An intermediary, if you wanted to have some downstream brokers, of which there are a few, making sure that replication to them is easy and simple. They don't have to learn stuff. They can focus on that science. An idea that I think people might want is just a smaller representation of things. So like right now, you get a postage stamp, and an alert packet is going to have, I don't know, 250 additional numbers. At some point, you are wondering about how many bits are in your summary statistics versus how many bits are in the pixel, and they are surprisingly similar. So maybe people want, less about that. This is a thing that's been under active development. I'm just presenting the original design goals, but we're to provide an alert database, to provide all the information that is in the alerts in a database format, because we talk about real time and streaming, but lots of times people just wanted to look some stuff up in a slightly more, I cared about what happened yesterday, but I don't need like minute to minute keeping track of that. Doing cross-matching, host matching for each event, like what do we know about it from other catalogs? So across surveys and then wavelength, radio to X-ray. Sure, an optimist will say neutrino, but let's leave that aside for just a moment. And then classification, and particularly replayable classification, and that we have a good enough version and configuration control that we can tell you why we made a classification if you want to later redo rates. We are not aiming to provide a data analysis platform. And that was a clear design goal. I agree with that, but that is complicated. I think sort of the stage we're in right now, if we need to start getting users, and the users ask questions like, well, what can I do? And it's like, well, you can get messages about stuff and then go here to do something. And so the ecosystem of brokers, there are other brokers providing some great things, including data analysis platforms. But we feel we have a unique and very open design, taking advantage of cloud infrastructure to make it easy for anyone to connect and understand what the system's doing. we don't have to run user supplied code in our system. Rather, the user can run their own code and connect in well-defined, easy ways to do that. So with that, I would turn it over to Troy to talk about all the great work and his journey, or as always, people don't care about the journey, the success. Hear the journey in the success. Go ahead, Troy.
Thanks, Michael. Appreciate it. Yeah, so I'm going to talk about the broker design, some of the challenges, the costs, hooking into the pipeline, things like that. This will definitely be tech oriented here. I think most alert brokers at this point are running at least partially in the cloud, whether that's Google Cloud or AWS. But nobody's doing it in the same way that we're doing it. Our architecture, our design is actually quite different from any other broker. So we're running with a cloud native architecture. So this is a microservices model. It's a collection of loosely coupled modules. These are running on Google's compute services, Cloud Functions, and Cloud Run. Those are essentially containers that are set up as HTTP endpoints. They communicate through public message streams through PubSub, which is Google's messaging queue service. And all the modules stream data into public data resources. BigQuery as a data warehouse with SQL access and cloud storage buckets for object storage. And so what this means is that it's comparatively easy for users to actually process the live stream because of the way that we are set up. And you can also query the past basically instantly. These are streaming inserts into things like BigQuery. Our architecture is very open and modular. You can connect in anywhere. And our use in particular of Google's data services, PubSub, BigQuery, cloud storage, makes it easy for users to use any of Google Cloud's tools and services. So even other brokers that are running in Google Cloud, the way that they're set up does not make it easy for the users to access Google Cloud's tools and services. So just a couple of slides, basic diagrams to kind of make the distinction here. So if we look at a typical broker architecture, they're probably running something like 3 clusters: consumer cluster, storage cluster, science cluster. A bunch of stuff happens in here, but basically you get the data coming out the other end after it's gone through the pipeline. By contrast, our broker looks more like this, and I'll fill in exactly what these things are in a couple of slides here, but this is just to give kind of a visual overview where to show that each of these modules actually runs independently. In between each of these modules, there's public-facing data resources. One thing, we have no clusters. We don't run any VM clusters in our broker. We have one single VM that's our consumer. Our ZTF consumer is very small, 1 vCPU, 4 gigs of memory. This is running a Kafka to PubSub connector. So all this is doing is taking the alert bytes and the metadata from the Kafka stream, passing them straight through into a PubSub topic, and that's it. The consumer doesn't open the packet, it doesn't do anything like that, just passes the Kafka stream straight through into PubSub. Once it's in PubSub, it's easy for the rest of our pipeline and actually anybody else to hook into it. So PubSub, what is PubSub? This is Google's streaming message service. You publish to topics, you pull from subscriptions. Topics and subscriptions are actually separate data resources in the cloud. So we have topics in our Google Cloud project. You as a user can set up a subscription in your own Google Cloud project that's connected to one of our topics. There's a few different types of subscriptions. The first one, pull from anywhere with an API. This is, if you're familiar with message streams, this is probably the way you're familiar with working with them, is to do a pull on the subscription. PubSub also offers push subscriptions, and this is really the key that makes this microservices structure work, or one of the keys that makes this microservices structure work. Cloud Functions and Cloud Run, again, are containers that are set up as HTTP endpoints. So the PubSub push subscription pushes to those endpoints. As far as I know, Kafka doesn't support push at all. And there's a third type of subscription that's fairly new that's called a BigQuery subscription. We have not put this into our pipeline yet, but I would really like to. The BigQuery subscription basically allows you to, instead of making an additional API call to push data to a BigQuery table, you can just publish it to PubSub. This BigQuery subscription will automatically route it into the BigQuery table. Once the consumer gets the stream into PubSub, everything else from there is running on an event-driven microservices model. So all the rest of the modules run independently on one of these serverless compute services, Cloud Functions or Cloud Run. This is per alert processing. There's no batching in our pipeline whatsoever. Each message is processed individually. And then each module, again, streams data into one or more of Google's data services. Every module publishes a PubSub stream, and then may also store it to BigQuery and cloud storage. So here is the architecture diagram filled out in a little bit more detail. So we've got the consumer just running the ZTF Kafka stream straight through into PubSub topic. So this is our current ZTF broker. The basic tasks of storing the alert data happen automatically right off the bat. We store the Avro files in Cloud Storage Bucket. These are immediately available. We also store in BigQuery tables. These are basically streaming inserts to a database. BigQuery isn't quite a database, but you can think about it that way. So these are streaming inserts. This data is also available basically immediately. And then we've got a few modules here in the science track of our pipeline. This Lightner module is the semantic compression that Michael referenced earlier. So this module publishes every alert, but a lightened version of the alert. So a subset of the fields in the alert packet that are deemed kind of most necessary. The next module is called the tagger. So what this module does is grabs some basic information that might be useful to filter the stream by and attaches it to the metadata of the PubSub message. So this might be things like basic information in the alert packet itself, and then maybe, well, it does a couple of basic categorizations. One is like a purity check, how many bad pixels and things like that. One is checking for likely extragalactic transients. So it takes all this stuff, it attaches it to the metadata of the PubSub message. And what that does is it allows you to put a filter on the subscription based on the stuff in the metadata. And then anything that doesn't pass your filter just gets dropped out of your subscription. So that's an easy way to kind of filter the stream. And then we have a supernova classification module here at the end. This is not our end goal here, but the supernova classifier was an easy one for us to get set up and running. We certainly intend to provide more of the standard classifications. So this event-driven microservices model, and this is basically PubSub plus Cloud Functions or Cloud Run. Some of the benefits of this, it's really lightweight. There's no cluster management, no VM management. You write an individual module that processes an individual alert, deploy it to Cloud Functions or Cloud Run, then it just sits there and listens to that PubSub stream and waits to get triggered. So the compute, Cloud Functions or Cloud Run, again, these are containers set up as HTTP endpoints. They scale from 0 automatically to meet the alert rate. So if there are no alerts in the stream, there are no containers running. If that alert rate spikes really high, a bunch of containers will start up in order to process everything that's coming through the stream. Per alert processing is easy to think about, easy to develop around. This is very fault tolerant. Any failures can be redelivered, dropped, or sent to a dead letter topic. And anything that happens to one message doesn't affect any other message. It's also really fast. The alerts tend to make it through all the way through our ZTF pipeline in 2 or 3 seconds or something. So this per alert processing is very, very helpful in many cases. There's at least one case where this is challenging. This per alert processing is challenging, and that is host matching. So what do I mean by host matching? Basically cross matching an individual alert to some catalog or catalogs. So like a nearest neighbor search for the closest star, galaxy center, whatever. So currently, host matching actually works just fine if you have a smallish catalog that fits into memory on one of these microservices. You can load the catalog into memory, use AstroPy or whatever, find the nearest neighbor, that works just fine. If you have a larger catalog, which we certainly will want to cross-match against, then what do? Well, there's certainly external services like CDS. Querying something like CDS 10 million times per night, once each for individual alert is not something we've tried to do. BigQuery, we would really like to be able to use BigQuery to do this type of cross-matching. So I tried this, ran into some problems with this. So I'll talk a little bit about that. So BigQuery is Google's data warehouse with an analytics engine. This is columnar SQL access. This has GIS built in, geographic information systems. So this is useful for nearest neighbor searches in RI DEC. It works, but it turns out that single point lookups in BigQuery are expensive. And this is in both time and money. So because our alert pipeline does per alert processing, we're trying to do single point lookups in these large BigQuery tables. It's just not what BigQuery is designed for. BigQuery is optimized for complex analytical queries on large data sets. It's kind of the opposite of a single point lookup. So BigQuery does a full column scan for every query. It has partitioning and clustering, but no indexes. BigQuery just doesn't use or understand indexes. So this is what makes the single point lookups expensive. BigQuery is undergoing ongoing development, as always. I'm not qualified to talk about any of that, but I have heard kind of murmurs of some type of indexing being added and things like that. So we can always hope that the BigQuery backend improves. One thing that we could do, though, to improve query performance against our tables would be to cluster by some spatial index. He'll pick order 5 or something. So Google BigQuery has other data sets in it. This is Google's public data set program. WISE is in there. There's ongoing work to get other large catalogs into BigQuery. We could certainly participate in adding more large catalogs to these public data sets, but we really need to solve the fundamental problem first before that would really be super useful for us. All right, so there's a bunch of things about our broker that are different than other brokers. One of them is the cost structure. So now I get to spend a couple slides talking about that. So the idea here, as Michael said so nicely, is to get the data into Google Cloud Data Services where it's just widely available, easily accessible. People don't need to rely on us for access or authentication or supporting a certain number of users or a certain certain loads. They can just go to Google, use any of Google Cloud's tools and services to get the data. We certainly can explore creating a public interface so that people can explore the data without having to authenticate to Google. But in general, users will authenticate and access data directly through Google Cloud. So that means that everyone's subject to Google Cloud's pricing structure, which is that everyone pays for what they use. So the pricing structure, basically, you only pay for what you use. No contracts, no pay ahead, just pay as you go for exactly what you're using. There is an ongoing free tier access. So each service has basically some small but reasonable quota that you can get for free. And then there's a couple of ways that you can get kind of one-time or maybe two-time credits. This does require a credit card just to verify your identity, make sure you're not a bot, but billing is not automatically enabled. So you have to explicitly enable billing in order to get charged. If you don't, then you can just use the free stuff and that's it. So a couple of examples might be helpful. So querying BigQuery, if you're a user that wants to query a BigQuery table, the free tier is 1 terabyte per month. After that, it's $6.25 per terabyte of data scanned by your query. PubSub is a little bit There's a little bit more detail here, partly because of sort of the difference between topics and subscriptions might get a little confusing. So it's worth spending a little time on. How it works. So the project that owns the topic pays to publish to the topic. The project that owns a subscription pays to listen to the subscription. The user that's trying to do either the publishing or the listening has to be authenticated to the right project, whichever project owns the resource, and that's how the billing occurs, is through the project. The actual costs, there's two, basically. One always, and that's the throughput. So this is cost on both ends. So it's throughput to publish, throughput to listen. 10 gigs a month is free. After that, it's $40 per terabyte. So this is just over like 10 million LSST alerts. Egress. So if the data has to cross a Google Cloud region, then they will charge you egress. If it doesn't cross a region, then there's no egress charge. So one thing that you'd want to avoid is sending a large amount of data a long distance. Those egress charges can rack up pretty quickly. You're better off doing a little bit of processing in the cloud and just sending out the data that you're actually interested in. The egress charges for some smallish amount of data should be pretty reasonable. No storage fees under the general settings. It's just basically the throughput, and then if you're into egress. All the Google Cloud services have a pricing page that actually I think does a pretty good job of explaining exactly what's going on there. All right, so a little bit of a summary slide kind of midway through here about what our current status is. We've been running the ZTF stream consistently since late 2020. We've also hooked into other streams, the ELASTiCC stream, which we'll talk more about here in a minute, the DCAT stream, the Rubin test stream, things like that. Our broker offers all of the standard technical services that brokers offer. We do it in different ways than other brokers do, but all the standard technical services are there with more flexibility in some particular areas and a different cost structure. Now, scientific services like classification is an obvious area that we could improve. Certainly in principle, anyone can add to our system. You can plug in and we'll talk more about that in the upcoming slides. But we certainly hope to provide standard classifiers across a range of science within the Pitt-Google Broker system. We know that people are definitely going to want some basic classifications, if for nothing else, just to narrow down that stream a little bit and get kind of the subset of things that you might be interested in processing further. So we've got some things kind of ongoing. Michael's working on a little microlensing stuff and some other things like that that we plan to support. So I have just a couple slides here about hooking into the pipeline, and this will segue nicely into what Chris will talk about is our preparation to participate in the DESC ELASTiCC Challenge, Dark Energy Science Collaboration's ELASTiCC Challenge. So hooking into our pipeline, you can hook in from the cloud or you can hook in locally. And through our participation in the DESC Challenge, we intend to demonstrate both access methods and how this actually could work. Hooking in from the cloud, you're welcome to use any of Google Cloud's tools and services that you want. In particular, our use of PubSub makes this easy. Because it makes it easy. So one kind of obvious thing that you might want to do is kind of the same thing that we're doing in the sense of write a function that processes a single alert, whatever kind of analysis you want to do, deploy it to Cloud Functions or Cloud Run. And that's an easy way to process the live stream with no headaches about managing servers or anything like that. You can store any results in the cloud, or you can send off to a local machine. So hooking in locally, Google has a UI access to everything through a web console, command line, Python, etc. Lots of other languages, access to everything. And I've also written a Python package, Pitt-Google client, that's basically wrappers around the Google API just to help facilitate the connection to our particular resources and also to simplify some tasks. Like, for example, listening to a pub substream, and then batch loading into a local database. And that particular thing is something that that DESC will use after we classify the elastic stream and send our classifications back to DESC. This is what DESC will use to load our classifications into their database. So I've got one more slide here before I turn it over to Chris, and this is basically an idea that I worked out when I gave a talk a couple of years ago to a group of multi-messenger astronomers. So there's a lot going on here. I'm not going to be able to talk about it in detail, but in general, this is how one might be able to do gravitational wave follow-up through the Pitt-Google Broker and Google Cloud. So the basic idea here is the astronomer would run 2 modules in the cloud. This first one over here on the left listens to the gravitational wave alert stream. This one would be always running, listening to this gravitational wave stream. When it finds an event that it's interested in, going to immediately deploy this second module, injecting the gravitational wave alert data into the module. And then this second module over here will listen to the LSST live stream, looking for possible electromagnetic counterparts, things that you might want to follow up on. In the meantime, this first module can turn around and immediately query the past. So it can query BigQuery, look for anything that LSST might have seen in the past that might be interesting. Both of these modules can then send their results out of the cloud into, maybe you're running a Tom toolkit or something, collecting all your data, triggering your follow-up and things like that. So these can send the data out through there and you can go on your way. So with that, I'll turn it over to Chris to talk a little bit more about our preparation for the Elastic Challenge. Chris, I'll let you take over the screen share here.
Great. Thank you, Troy. Okay. Troy, can you give me a thumbs up if you're able to see my screen? Okay, great. Thank you. So hello, everyone. My name is Chris. And as mentioned previously, the Pitt-Google Broker has been a participant of the Elastic Challenge. And over the next few minutes, I'm going to talk about the process behind designing, developing, and deploying a supernova classifier for the Elastic Challenge. There we go. So the process behind designing the classifier module revolves around answering 3 essential questions. The first being, how do I receive alerts for processing? And the answer to that question is relatively simple. We're going to take advantage of the services provided by the Pitt-Google Broker. So within the Pitt-Google Broker's Google Cloud project, we have a consumer virtual machine, which we've called Elastic Consumer. This virtual machine listens to the live alert stream that's being published to a Kafka topic, and this Kafka topic is being specified by DESC. Once the consumer ingests the alerts, these alerts are then pushed to a pub/sub topic, which we've called Elastic Alerts. So we can take advantage of this and go ahead and create our own external Google Cloud project. And we can listen to the messages that are being published to the Elastic Alerts topic by creating a pub/sub subscription. And as you can see in the diagram to the right, the Elastic Alerts topic is able to have multiple subscribers. And so after each subscription subscribes to the Elastic Alerts topic, pub/sub guarantees that each subscription will receive every message at least once. But one of the key features here about pub/sub that we'd like to take advantage of is the fact that we can use these subscriptions to trigger our classifier, which is going to be run using Google Cloud Run. So we've answered the first part of our question, how do I receive alerts for processing? I think a very important follow-up question is, how do I deploy my classifier? And so let's take the example of the open source photometric classification software, Super and Nova. I'd like to, use this software to classify the alerts that are being published to the ELAsTiCC topic. I can package this software by using Docker. And so I'll walk through that process. The process of deploying Super and Nova to the cloud involves creating a script that contains all of the information to assemble a Docker image. The Docker image is going to contain the source code, as well as any other additional code or parameters that are necessary to participate in the Elastic challenge. We're going to containerize that image and deploy the containerized image to Cloud Run. And so, as I mentioned previously, every time a message is pushed to the subscription, or I guess the better word would be pulled, every time we get an alert in our subscription, we're going to trigger the Cloud Run module, which contains our classifier. So this is going to process the alert and classify the supernova, or give a predicted outcome of the supernova type. So Cloud Run is a scalable serverless product. And we really like taking advantage of the fact that Cloud Run is scalable. As Troy mentioned earlier, we have a very large demand of alerts at times. And so it's important to be able to scale to meet that demand. And so Cloud Run allows us to automatically increase the number of container instances to meet the demand of alerts that we need to process. And I'll note also that Cloud Run responds to web requests and events like alerts. Great, so we've reached a good point of, we've made a lot of progress in developing this classifier. I'll give a brief rundown. So again, the ELAsTiCC topic is pushing, the ELAsTiCC topic is receiving alerts. We've created a subscription that's going to pull those alerts, and those alerts are going to trigger our classifier. Lastly, we'd like to figure out a way to store the classifications once they've been classified. And so that process involves publishing our classifications from the Cloud Run module to the pub subtopic, which we've named Elastic, Super, and Nova. Subsequently, we're going to write those classifications to a BigQuery dataset and table. So this is an overview of the pipeline that we've developed in order to participate in the Elastic Challenge. You can see in the top right corner what those classifications look like. So we have an object ID, a source ID that's taken from the metadata of the alert. You can also see two columns that indicate the probability that the object is either a type 1a supernova or not. So probability class 0, or I guess specifically 0, indicates the probability that the object is a type 1a supernova, while class 1 indicates a non-type 1a supernova. And you can see the predicted class at the far right column. So in the upcoming months, we're going to continue participating in the Elastic Challenge. And as Troy mentioned, we're working on publishing those classifications back to DESC. And so with that, I'd like to say thank you, and I'll conclude here. If anyone has any questions, please feel free to ask away. I'll continue to share my screen in case anyone wants to point to a particular slide, and I'll hand it over.
All right, great. Thank you. Thank you. Okay, so we have very good questions in Slack. Okay, so what I will do, I will ask the first question. I will use that privilege and raise your hands. If there are no hands, there are very good questions in Slack, or the people who have questions in Slack, you can raise your hands. So what I would like to start with, and it's Troy, you were saying, for instance, the problem is with cross-matching. And for instance, you were talking about, oh, so we can just use HipScat order 5, which is something, this cross-matching is really what we have been doing a lot in LINCC, and you try to do HipScat in some shape, basically. But still, like, how would that work? You would still need to know which file. I presume you like to split the sky into 100 files or many files. That's kind of what we do. But you will still have to know which file you have to load in memory. You know, you will have like 1,000 files. They're all loadable into memory, but how would you still know which file to kind of query or load into your microservice? Do you understand a little bit what I'm saying?
Partially. So you're asking about using a HipScat catalog
That's
to
you
cross-match against
mentioned
the live stream.
Right, you mentioned that as a possible solution,
Oh.
but there is still another obstacle, I feel, because how do you know what to load into your microservice that it's
Yes.
in memory, kind of?
Yeah. So the thing that I mentioned with HealPix order 5 was actually that we could cluster our BigQuery table by some spatial index like HealPix order 5,
Right.
and then that would make up queries against queries against those BigQuery tables more efficient. And so
Right.
that
So you
may
would somehow batch, basically.
No. So
No.
so right now I'm not talking about HipScat or Parquet or
Right.
anything. I'm just talking about one of these microservices modules
Okay.
doing a cross match against BigQuery, but that clustering of a BigQuery table is something that we could do to make that query more efficient.
Got it. I think I get it.
Yeah. So if you, but I can say something about using something like a HipScat catalog. Yeah. So maybe I'm not sure how much everyone on this call quite knows about HipScat. That's a work in progress by the LINCC group to put large catalogs into Parquet format and partition by a variable order HealPix. So denser regions of the sky will be partitioned at a smaller scale, higher resolution. So you basically end up with all these Parquet files that are organized spatially. So yeah, if you wanted to think about using those files in a pipeline like this to do the cross matching, probably what you'd have to do is the incoming stream, whatever topic you're listening to, would have to be separated by region on the sky, so that you could have one module just listening for this region on the sky, and it would have those files loaded. That type of separation of our PubSub streams, separating spatially to make something like that easier, is something that we've discussed. We haven't done any development towards it, but it is kind of an idea that's out there that we've discussed.
Okay, yeah, exactly. Okay, that you see exactly. There's another layer here, right? That was my question.
And in broad principle, BigQuery's blanking clustering bits is sort of supposed to be able to do that in a flexible way. As often, if you know some more specific things, you can get better performance than doing that. So our preference would be able to use BigQuery to do this. But I think certainly a very practical thing is saying, hey, we know actually what LSST just observed, what it's about to observe, what's going to observe in 10 minutes. We can spin up a bunch of VMs that have those small catalogs loaded and make those lookups fast. Like that's another direction we could go.
Okay, then I see for so many questions in Slack, which Tim, do you want to ask them, or I can just read them out? So for instance, the first one was like, does Kafka provide any guarantees of message delivery?
So I'm not exactly sure what all of Kafka's guarantees are. There might be somebody else on the call who knows more about Kafka than I do that could answer that.
Okay. Okay, that so to be investigated. Okay. So Colin, do you want to ask your question which you had in Slack channel if it wasn't really answered, or?
Yeah, that's fine. I just was curious if there were specific science cases with the dollar figure at the end of those science cases for different scale or different scopes of science projects. I'm just trying to imagine like how this is going to impact if people trying to do different science and at different types of institutions.
Yeah, let me try and, oh yeah, I have it right here. Chris, let me grab the screen share here. So this is a slide that I put, so for the talk that I gave a couple years ago on multi-messenger astronomy, I put together a cost estimate for that last slide that I showed, which was the multi-messenger gravitational wave follow-up. So the cost estimate for what's in that slide looks basically like this. So yearly, that's like $810, and this includes some specific thing, the 2 Cloud Run instances. Whoops, I'm sorry. The BigQuery queries, and then the PubSub stuff. I could also show you a slide that is our ZTF broker's charges for last month, if that's helpful. That'll give you kind of an idea of what we're paying to run that ZTF broker, which would obviously be more than a user like you would do. So I thought I'd start here with this. But I could show you that as well.
So for instance, in this user analysis, it's a little bit hard to tell what is actually the largest kind of hit that you are.
Yeah, well, for this, it's probably the BigQuery stuff. So nightly, it's the way that I've got it set up here. The BigQuery query charge is what's largest here.
And
it really depends on
less expensive earlier on and way more expensive at year 10.
Yeah, so I mean, it depends on exactly what you're doing. So if we look specifically at the BigQuery cost, so again, BigQuery does a full column scan for every query. And so if we put in some of these, if we structure our BigQuery tables a little bit differently, for example, with that HealPix order 5 clustering, then you can reduce the amount of data that query has to scan. And so you could reduce some of those costs so they don't grow as much over time. But certainly, yeah, at year 10, there's going to be a lot more data in BigQuery that you might want to query. And so those query costs might be a lot higher.
Just to interrupt, it depends what you're querying. So
right.
There's more data if you think about each subtraction DIA sources, right? But in terms of the object catalog that you're doing a cross match against, that density only is going to go to square root of year, right? It's going to go to square root of exposure time, like just hand wavy. Just to sort of help people who don't maybe think about astronomy, right? Like the catalog goes as numbers of text objects, right? But like the signal noise goes as the square root of the time. So it's not going to go up by 10, it will go up by 3 or something. It is always the case, and I think this is the issue, that you could accidentally do expensive things. So that's certainly a thing we want to avoid. And I'd like to just say one sort of philosophical thing. Practical and philosophical. Philosophically, you can run your own classifier, you can listen to any module, it's going to be great. In practice, look, if you're running a classifier and you're willing for it to be shared, we're happy to add that to our list of things that we're managing and maintaining, because one person maintaining 10 classifiers against stupid little things that might break is much more efficient than 10 different people who don't think about this much, maintaining that. So I anticipate there will be such a thing. Now, actually, just to be clear, right? You can run your own classifier and write your own proprietary tables and not share that with anyone. It's totally fine. Right. So one of our goals is to get out of doing user authentication or groups or having to determine how you share data. Like you can just sort of do all that. I wanted to invite, sorry, Nevin, I wanted to invite Tim specifically. Do you want to ask a question about something that didn't work or some painful thing Troy would like to share so you appreciate his journey?
Can you hear me?
Yeah.
Excellent. Partly it's that. I mean, we're not heading down exactly parallel roads because there's a set number of downstream brokers for Rubin. But it was sort of something Colin Chandler and I were also sort of talking about, is that the dead ends, missteps, and the technical way, the weighing up of technical solutions is usually airbrushed out of scientific papers, and you never get to hear about the stuff that didn't work. And particularly for this sort of stuff where you're applying tools and techniques that have been developed for other projects and other research areas into astronomy, I find it's helpful to know what did and didn't work for people, and why.
Yeah, so I'm not sure if there's a specific question in here. The biggest thing that we ran into that would be a common thing that you might want to do that didn't work was that per alert cross matching against BigQuery that I spent some time talking about. Yeah.
Sorry, if you have things, please go talk about. Maybe
no, please.
Like the evolution from functions and data flow to Cloud Run, and maybe some of that might be an example.
Oh, yeah. Okay, so I think what you're referring to is so early on in the development. Well, I guess let me say first, it was always Michael and Ross's idea to have this microservices model that we're in now. When I first started actually doing the development on it, I was new to basically all of this stuff. The microservices thing just confused me for some reason. It was a lot easier for me to think in terms of a more traditional data pipeline. So I started using a Google product called Data Flow, which is just a more traditional, the data comes in to a single place rather than separated out over all these individual microservices. It comes into a single place. You do your processing in a much more traditional way. At the beginning, that was easier for me to think about and to write up. It turned out to be not very efficient and caused a lot of sort of dependency issues and having to work within that particular structure. But once I had it set up, and I thought again about this microservices model, it was a lot easier then for me to think about how the microservices model worked and how to translate that. And so I transitioned us into that microservices model because of our well, let me not go down that road. But yeah, so it turned out that traditional data flow type model was much more cumbersome to develop and to run, less efficient in compute time, in cost time, and things like that. And the microservices model just runs so much more smoothly. It's easier to think about, easier to develop, easier to swap pieces in and out because nothing kind of depends on each other.
Thanks. I guess a sort of related and sort of more general question is also, what issues have you found with applying BigQuery to astronomical data sets, which tend to be indexed very differently to the sort of stuff that BigQuery is normally used on, because astronomers tend to, we can, rightly or wrongly, we consider things as indexed on the sky in 2D spatial GIS type coordinates, which is not something that the big data analysis platforms normally think about.
Yeah, so the BigQuery capabilities are an area that we've just kind of dipped our toe into, or I have just kind of dipped my toe into a little bit here, but certainly I have not explored the full power the BigQuery and doing the types of complex analysis on large data sets that it's really good for. And so there's a lot more to be explored there, but with the partitioning and clustering that BigQuery does allow, so the clustering in particular should be designed to help with some of this type of stuff where you can cluster tables by groups of columns that are common things that you might want to query against, like Raen, for example, a spatial index that can help speed some of those things up.
This is one specific answer. Storing like HTM20 or something is actually a pretty relevant thing to at least make some sort of simple numerical bit.
Okay. I was interested, Michael, if you could okay, Costa, please, Costa.
Oh, sorry, Raen, to interrupt
No,
you.
of course.
Thank you. Hello, everyone. Thank you so much for your talk or talks. I'm not sure how to tell them. I have, a question from a user perspective. So let's say that I would like to run my classifier, which is not for every object happening on the sky, yes. And I have two things I don't understand here. So from the pipeline of point of view, could I pre-filter part of the data on your side before consuming the stream? Yeah, because you said that $40 for a single night of LSST alerts turns to something like 10,000 per year, which sounds a bit expensive. And the second question is coming back to the discussion about batching, because all these ML models, they all written or have some buzz code of in Python, yes, and it's not so efficient to run. It's not even because of Python, it's because of many things. It's not very efficient to run them for any single object. So it's not only cross-matching issue, I mean no batching, yes, but also evaluation of people's codes, especially for machine learning. Yeah, so you wouldn't load your single object to GPU memory, for example, because it would take so much time, yes. And without batch processing, it could be much slower. Yeah, so again, if I do it with no batching, I lose a lot of computational time, resources, latency, and money. Yeah, so these two questions.
Yeah.
First, pre-filtering, and second, could we do anything about no batching?
Yeah, sure. Thanks for your question. So the filtering, yeah, so there are a few different places where filtering can happen, and certainly we don't imagine the end user having to process every single alert that comes through from LSST. Yeah, so we certainly imagine that users are going to want to process a much smaller version of that. So one place that filtering can happen is through our pipeline. So we certainly intend to offer a range of classifiers, and the modules that publish streams from those classifiers could, in principle, publish just a subset of the alerts that actually are deemed to be likely supernova or things like that. My goal would certainly be to have any module in our pipeline that actually filters out alerts to value completeness over purity, just so that we're not immediately filtering out anything that you might want to look at as a possible supernova that's kind of on the edge. So that's kind of the first area that filtering could happen. The second area that filtering could happen is when you create a subscription, you can put a filter directly on the subscription using whatever we put in the metadata. So that was kind of the tagger module that I talked about. That's the point of that. So your subscription can then just automatically drop anything that doesn't pass your filter there. And then the third place that filter could be implemented is on the user side. If what's in the metadata and what we've done in the broker side isn't enough filtering, you can just put your own little filter in there to just pass through anything that you actually want. So that's kind of the filtering bit. The batching bit, yeah. So we've let's see. The microservices model, basically, if you use Cloud Functions and Cloud Run, those are per alert processing. That's just how they work. They're HTTP endpoints that get a single alert that triggers it. But yeah, you're right. There's plenty of use cases where batching would be helpful, and there are other ways that you can do it. You just wouldn't use Cloud Run or Cloud Functions. So you might have a VM. You could either use a Google Cloud VM or one on-prem. But what you might do is listen to a pub/sub stream and then use that Pitt-Google client package that I've written that includes that bit about batching pub/sub streams. So pub/sub itself is massively parallel. Pub/sub itself doesn't allow any batching natively, but this Pitt-Google client that I've written is just a thin wrapper around that adds, one of the things that it does is adds that batching functionality. And so that's what DESC will use to batch load our classifications into their database. And so you could do the same thing on a VM anywhere to collect a batch of messages and then run them through whatever processing you want.
Great, thank you so much.
Yeah, thanks.
Okay, any more questions? Can we maybe, yeah, Eric, please.
I was just curious about how much smaller you're able to make the packets in your Lightning approach right now, and how you feel like that tuning has, there are obvious trade-offs there one way or the other.
Yeah, that's a great question, and I just don't have that number off the top of my head. I could certainly get it to you, but I will say that what's in there right now with Lightning, we're really just passing through the basic things that other things in our pipeline use, so that the downstream modules in our pipeline. There's certainly room for a much larger discussion, both within our broker and within the community, about exactly which of these things are useful and we want to pass along. So right now, I think we're passing along a fairly small subset. That's certainly an area for more discussion.
Thanks for that question, Eric, because I think a general question to all the brokers and the classifiers is basically, okay, you've all been running, you've had ZTF, you've had Elastic. What did you not use? Like, that seems like an obvious starting point. Once you start doing a couple different types of classifications. And that way of phrasing the question hadn't crystallized. Thank you.
Could we maybe finish, Michael, with very short, a little bit summary of what you wrote in Slack about how user would write a package and a little bit, I think that's very interesting. And maybe if you could just summarize it for the record.
Yeah, so Chris worked last term to add SuperInnova as an example of how to add as a user. It's unprivileged, there's no specific privileges to the project. And it's just running SuperInnova, just as that example. And so I'm taking that now and trying to add, I don't know how to pronounce it, microlensing bit, and sort of understanding the structure. And the basic structure is very simple. It's based on if the package is published to PyPy, so we can capture everything we need in requirements.txt. Then we can do a Docker build of that. Run cloud build. Troy's going to correct a few things I say wrong here, but conceptually, I think this is right. And you just run cloud build, and you just specify that you have your requirements to that. And then you just have a little bit that's going to load something from that package. One common thing you're going to need to do, and this is a general versioning question, is often if something has a trained model, or even if it's a functional and has set of parameters, you need to preserve those separately because that's not uniquely defined by the software version. Or the software version itself probably doesn't come with those as you want to use those. So you do have to capture that separately and write that up and just have some like main.py is what it's called. But I mean, run whatever, right? But like just some simple, the VM starts up, it runs this thing, it produces the output, it puts back. So we'll have a couple of templates to try to set that up to make that pretty clear. It says, put in your thing here, and do that. And the question of Rachel asking about that again, I actually wrote some issues as I have from other people's questions about this. So that's a little bit of a jump, right? Like someone's used to writing their own code and doing it, and it seems a little bit to do the Docker build. But if you just publish a pipeline, and we just write a requirements.txt, then actually the building and deploying the container is surprisingly simple. Sure, it's magic incantations, and that's fine.
Yeah, and you said publish to PyPy a couple times. I don't know what you mean there. There should be no reason that the user needs to publish anything to PyPy.
It is an easy way to make sure that your package is in there when you specify in your requirements.
Oh, I see. So you're talking about getting the classifier package from PyPy rather than loading whatever classifier model you're. Yeah, I see. Okay. Yeah.
Yeah, and I was mixing the idea that the user is most likely a developer of a classifier.
Yeah. Okay.
If you're just
Yeah.
using something that's already published, sure, like it's already there. That's what I was saying.
Yeah. Okay.
I mean,
Yeah.
yes, you don't have to do this. You could add all your code in there as part of the runtime, but don't do that. That's gonna be annoying to test.
Okay, great. Barring any last questions, this was great discussion. Thank you all. Next talk will be in September 14th, because August slot is strongly overlapping with project community workshop for LSST. We haven't announced the September talks yet, but we have several very good talks. We are just putting where will they be September, October, November. So, you know, have a nice summer. I hope to see many of you at the project community workshop, and see you, stay tuned, and see you again in September. Thank you. Thank you all.
Thank you for hosting us.
Thank you.
Thank you. Bye, folks.